Hey, it's Libby here. So we figured out the position for A, and A's great, but to figure out the position of B, well, it's kind of frustrating because really what we need to end up doing is figuring out what position we're at right here. So we're going to use this as our initial position. So where in the notes you see it has that 1/2 3 meters per second squared times 1 second, that's them kind of doing a shortcut to figure out that position right there. We're not going to take that shortcut. We're going to go ahead and do it together. And so for A, we see that the initial position was 0, the initial velocity was 0, and the acceleration was 3, and the time was 1/2. This time, to get the position right here, we're going to use almost the exact same information, only this time we're going to carry that. The time is going to be different. The time is going to be 1 now because this line segment goes all the way up to 1. And we need to figure out the position here to use that as the initial position for B because it's the start of a new line segment, and it just kind of makes it easier since it's a straight line. So where that 1/2 3 1 squared came from was when they did this. They said, and I'm just going to call that my X position at 1 second, just to kind of, and that's what that little 1 down here means. It's just that it's the X position at 1 second, just to kind of, we're going to have a lot of X's, and having things like that, these little subscripts just make it easier. So we already looked, I didn't draw the other graphs, but if you remember from the other graphs, the initial position of this line segment is 0. The initial velocity of that line segment is also 0. Now, the paper got a little lazy. Technically, they should have the time in there. I'm going to put the time in there as 1 second, because we're also, don't forget, we're trying to find the position at 1 second. And we're going to add that to 1/2. And then the acceleration from the graph we saw was 3. And then the time we're trying to find this position at is at 1 second squared. So it's this segment right here that's the first term in the equation you see in your problem, because they kind of just cut all this stuff out because it ends up being 0. And so I'm just going to say that the position at 1 second is 1/2 times 3 times, well, 1 squared is 1, and so we just get 1/2 of 3, which is 1.5. So the position, as I said, right here is 1.5. We're going to use on probably meters. Let's just be legit and put meters on there. So we're actually going to use that. Let's see, this is kind of a new, I'm still getting used to how this thing works. Oh, okay, I can move that up, but I want to move the whole thing up. Okay, we're going to, sorry, still working out how to figure this out. Doot. Oh, here we go. Oh, there we go. Figured it out. Okay, so now that I know how that works. So this up here is when the velocity changes. And so we're going to use this 1.5 as my initial position. And so when we go for our equation, and now we're going to find what position we're at B. And if I'm looking back up here and I call these my template equations because it's just an equation, I'm going to put things into it. My initial position now is going to be this 1.5 meters, because that's the initial position where this line segment starts. And so my initial position is 1.5. And now we have to go back to the second graph, which I'm sorry I didn't draw, but it looks like that in the second graph, the velocity, the initial velocity for this line segment is the initial velocity for this line segment, never mind, I got the graphs wrong, sorry about that. It's a little rusty, it's summer, I'm sorry. But the initial velocity for this line segment is 3 meters per second. And let me be good and write down that this is in meters per second and this axis is in seconds. So that means that my initial velocity is going to be 3, and my time goes in next. Now, since we're trying to find the position at B, we're going to use the time that B is at. Well, B is at time 1.5 seconds. But since we're starting our position at 1.5 meters, I can't say that I'm using a total of 1.5 seconds. That's using the entire part of the graph right here, and really we're just talking about this little section right here. So that's why in your notes it says 1.5, let me see if I can zoom out, there we go, that might help, 1.5 minus 1, and that's how we get the time for this segment right here. And now we're going to put in the acceleration, which is 1/2. And then if we look at the second graph shows us the acceleration, and the second graph, the acceleration is 0. And my time is always going to be the same, 1.5, and it doesn't really matter because since this is 0, this whole thing just kind of goes to 0. And so that's why for xb, or the position at B, you get 1.5 plus 3 times 1.5 minus 1 is 0.5. 3 times 1/2 is 1.5. Sorry, I'm using my finger and so it's a little weird. And that's why they get that the x position at B is 3 meters. At least they should have, did they? Woo, I didn't mess that up. Great. So that's the x position at B. It really kind of sucks that they keep on giving you these positions that are halfway through each line segment because they're really just making you do this equation multiple times. And we're kind of going to have to do the same thing to figure out C. Because while I figured out the position at B, we really need to know this guy because he's the beginning of the new line segment. And we really need to keep all of our equations based on line segments because that's on these line segments the acceleration is the same, and so we can use that. If you cut from, let's say you wanted to figure out, since we figured out B, let's say you just want to go, can I just go from B to C? Yes, technically you can, but that requires calculus-based equations, and these equations are algebra-based equations. And in algebra-based equations, the acceleration cannot change. And if you look at the graph from the second graph, sorry, from 1.5 seconds to C is at 4 seconds, the acceleration changes. We can't use this equation. So that's why we're sticking everything to these specific segments right here, because that's where the acceleration changes. So now we get to go through and do the lovely job of figuring out, ooh, lots of stuff. I'm so sorry about this. Now we get to go through and figure out x at, was that 2 seconds? Let me double check. Yes, x at 2 seconds, because we're going to need that to be the initial position that we're going to use for our equation to figure out C. It's a lot. I'm sorry. I hope this is making some sense. So anywho, the initial, where are we at for that? Okay, sorry, I'm looking at C really quickly. Okay, so what C is doing is we're figuring out the 1/2 times 3. What is going on with C? Hold on. I'm going to pause this for a second. I had B figured out, and I thought, oh, C is going to be a cakewalk, but I need to take a second to look at it. I'm going to pause. It's not going to be any time for you. Okay, and I'm back, and I'm ready to rumble. So to figure out the position at time 2, which let's take another look at this graph. Time 2, right here. The initial position for time 2 is when x is 1. So that's 1.5. If you look on the notes you sent me a picture of, on XC, there's 2 different parts that have a black pin underline. Both of those 2 parts are how you get the position at 2. Instead of doing it within the equation for C, I'm just breaking it up to show you where it came from, because they simplified out some of the zeros and things like that. And so when you just look at the equation, it's super duper confusing, but it's just because they simplified out some zeros and didn't really tell you where that stuff was coming from. So instead of skipping all that, we're going to just spread it out. I always am a big fan of taking things in little chunks and calculating what I can, instead of putting everything into one huge equation that I have a degree in physics and a minor in math, and I still sometimes get lost in it. So there's no shame in this game. But for x of 2, the initial position for x of 2 is going to be x of 1. And we've actually already calculated that. X of 1 is 1.5 meters. So we're going to go on ahead. Oops, there we go. Did I delete something? No. X of 2, with the initial position of x of 2 being 1.5 meters. And then we have the initial velocity, which is 3 meters. And from x of 1, where this line segment starts, to x of 2, that is a time of 1 second. And then the acceleration at this point is 0. So I am gonna do what I said I wasn't gonna do, and I'm just gonna not write the 0, because we've talked through it and I'm running kind of out of space. And so 1.5 plus 3, that's 4.5 meters. And so I know that the position, because don't forget, this graph right here is just velocity. And so, but I know that the position of the car at this point right here is 4.5 meters, which is going to be my initial position I'm going to use to figure out C. Okay, so, scroll on down. X of C, initial position is 4.5. Initial velocity, well, let's look at the graph. The initial velocity looks like it's going to be 3. And its C is at 4 seconds, but we're starting from second 2. And so they just went ahead, and in your notes, they just wrote this as 2, but that's where the 2 comes from. We're going to 4, but we're starting at 2. And now I'm going to start writing it down here. We have the half times the acceleration. I'm going to just read off the second graph. It looks like the acceleration for C, is that 3? Negative 3? Oh, negative 2.5. Ooh, yeah, halfway between 2 and 3. So the acceleration is negative 2.5. And as we said, the car travels all this stuff in 2 seconds. And so that's 2 seconds squared. I again got lazy. This is where this comes from. I just was running out of space. And so I like to simplify this thing on up, where we have x of C equals, well, 4.5 is as simple as that's going to get. 3 times 2 is 6. Okay, 2 squared is 4. 4 times 2.5 is 10. Half of 10 is 5, and oops, it's negative. So that's going to be negative 5. And so x of C is 6 minus 5 is 1. 1 plus 4.5 is 5.5 meters. And let's hope that that's what they got on the notes. Oh my gosh, it is. Sorry, I was actually really proud about that one. Okay, so I'm sorry this is so long. I really hope this works. If you have any questions, just shoot me another text. And if there's like a specific point you have a question about, just tell me what like time it is, and I will be more than happy to look at that. I don't have much else going on. Anyhow, I really hope this works, and I will hopefully talk to you soon. Unless, well, if I don't talk to you, it's because you get it, and that's actually pretty awesome too. Have a great rest of your evening.